And clarity, okay. So I work at NYU at the math department and the Center for Data Science, and I'm looking at this problem from like a data science point of view. So hopefully this will settle something. We're interested in optimization problems that come from data science and machine learning. These problems are usually NP-hard, but NP-hard is a statement about the worst case instances of your problem, and sometimes heuristic algorithms do a good job in typical data, and so there seems to be a gap between the theoretical guarantees and the practice. So we are interested in understanding what is the structure that makes the algorithm work. And the data science philosophy is we don't care if a problem is NP-hard, we just want to solve it. Sometimes you can find the exact solution or a very good solution for NP-hard problems in a significant subset of the problem instances, like in compressed sensing. There's this thesis that says that clustering is difficult only when it does not matter. That is also controversial, but we are trying to see what can we add in this direction. And this data that we're looking at is not adversarial, it's just some data. So when looking at theoretical guarantees for clustering, from like a data science point of view, you have these probabilistic models for your data that you can analyze your algorithms in expectation or in high probability, like what Dustin did with the stochastic ball model and with mixture of Gaussians. But real data is not random, it doesn't satisfy your model, so may not be useful for a practical point of view. Even though understanding how your algorithm performs in these models is a sanity check, is useful, because if you know that your algorithm doesn't even work in the simple cases, you cannot expect it to do something good in a more real case. And there's also these deterministic conditions for clusterability that Shai was just mentioning earlier, and he has a few papers analyzing them. And these notions of like clusterability for data are nice to look at, but sometimes they're hard to test, like center stability or perturbation robustness. And they're maybe not realistic for the data that we have. So data cannot and also maybe your clustering objective is not actually just like finding 10 clusters, but it's more complicated. You have a harder problem that comes from your data. And your idea is that, okay, I should only do clustering if my data is clusterable. But how can you evaluate that your data is clusterable? How do you know if you're getting optimal clustering from your algorithm? And KMeans Plus doesn't give it, and I'm going to show a way to give it in a data-driven way. So in this talk, I'm going to talk about KMeans clustering. There is this algorithm, KMeans Plus, that everyone uses, and it's amazing, and and Dustin just explained it. And then there is this semi-definite programming relaxation that has guarantees that also we just saw, and has guarantees for specific models. And in my talk, I'm going to talk about a technique that leverages the guarantees from the semi-definite program to produce a sublinear certifier of approximate optimality of solution, and this requires no model in your data. So
like sublinear in what?
In the number of points.
Like sublinear time and the number, or sublinear
size? Time in the number of nodes, in the number of points that you want to cluster. Yes. So we don't require a model. So okay, so we have the KMeans problem again. So you want to minimize the sum of the distance square between your point and the center of the cluster. Here we are in Euclidean space, but see. So this problem is NP-hard in the plane, and there's the Lois algorithm that we just saw. You choose k-centers at random. You assign each point to the closest center. You recompute the centers, and then you do that again until convergence. And KMeans Plus is just a smarter way of initializing this same procedure. So the KMeans Plus is fast, is very easy to implement, and is widely used. And in my point of view, I think the the worst problem that it has is like given the output, it doesn't tell you how good as a solution it may be. So it may converge to a local minima, or it may converge to the optimal. You don't know how do you evaluate how good the solution is. And this is what I'm going to do. So we have this semi-definite relaxation that we just saw. So I'm not going to go much into it, but it's like this optimization problem where X is, you're looking for a matrix of this form that is going to indicate your clusters, and you solve it with this optimization. So my goal is to find a lower bound on the KMeans value. So I run KMeans Plus, I get some clustering, and I want to know how good this is. So I'm going to say, if I have a lower bound saying that, well, the value of your clustering can be at most something, then if your KMeans Plus value was very close to it, then you know that it's almost optimal. Yes?
So how do you define close? Because
okay, yes, we're gonna look into that. Yes. So so far the only lower bound for the KMeans value that I know is the one that is given by the KMeans Plus original paper in 2007 that says that if you have a bunch of points that you want to cluster and you consider the random variable W, that is the value of the KMeans Plus initialization. So just like in his plot, like the first step, then the value of the KMeans is going to be 1 divided by the number of points times the KMeans value, and this is going to be greater or equal than 1 divided by 8 log k plus 2 expected value of this initialization. So this tells you that the value of the KMeans needs to be greater than this lower bound. This is the lower bound for the KMeans value. So this lower bound, let's test what this lower bound tells you. You will run it in the MNIST training set with 10 clusters, and we ran KMeans many times, and we obtained that the lowest KMeans clustering value that we obtained was 39, and this lower bound tells you like 2.15. So my question is, can we get a better lower bound than that? So the idea to obtain a better lower bound is quite simple. The idea is that, so your KMeans objective, if you have these points and you have 4 clusters here, the KMeans objective is going to take every point and you're going to sum the distance squared to the centroid, and then you consider the average of that. And if you take a sample, like a sample of your points, then what happens is the sum from each point to the new center is going to be like smaller in average. So when you sample the distance to the centroid, because the previous centroid is also a feasible point from your optimization problem, so this minimum is going to be at least as good. It's going to be smaller. So in math terms, what I'm saying is that the value of the SDP in my sample is an expected value is, well, in general, the value of the SDP in the sample is smaller than the value of the KMeans in the sample because it's a relaxation. And then I'm saying that the expected value of the KMeans in the sample is a lower bound for the value of the KMeans in the whole set. And my goal is to establish that the expected value of the SDP in the sample is greater than some bound with small p-value. So that's my goal, to give a probabilistic lower bound on that.
Once more. Why is the value, I mean, say I solve are you claiming that if I solve the sample optimally and look at the cost, it's going to be a lower bound to the optimal solution to the whole data set?
Yes, when you divide by the number of points, yeah.
In expectation?
In expectation.
Right, because I can, right, so what do you mean in expectation? Where do we take the expectation?
Here, so.
The expected over all samples of the value in the sample. Mm-hmm. Right, but the expected over all samples of the value of the sample is the true minimum, isn't it?
No, because you recluster, you pick a different center, right? The center is like dependent on the sample.
I know.
I mean, that's what she's claiming.
Yeah, I know, but I have a paper that shows that it converges to that the expectation of a sample converges to the truth.
Maybe this is the
As the size of the
assumption, that's
sample
equality.
goes up.
As the size
Yeah.
of the sample.
So fixed
No,
size of the sample.
no, fixed expectation takes care of
But
it.
and with no assumption, it's equal. She's saying it's always like smaller equal, and you're saying it's equal, or maybe there are like some extra assumption to get equality.
Yeah.
Like if you have all the points like in one place and one point somewhere else, if you don't sample that one, then the value would go down
Or if you
significantly.
sample K points.
In one cluster. If you miss one point, it would immediately go down significantly.
Right.
Yeah, if you sample K points, then the
Yeah,
value
yeah.
is 0.
Okay.
So let me show you how this lower bound performs. So here, this blue line over there is the KMeans plus value. This is the KMeans plus lower bound with the expected value of the initialization. And what we plot in red is the value of the SDP in the sample, and then we take this the expected value. So over these experiments, that's like the maximum, the minimum, and that's the expected value. And that lower bound, you can just take 100 points, and it provides a pretty good lower bound on the value of KMeans. And if you fix the number of samples that you're going to use, then this runs in linear time. So you can just see how many. Well, if you do this experiment, you can just given time budget, you can decide how many samples you want to do and how many experiments you want to do. Yeah. So the lower bound is pretty close, and so for this data set. And the useful thing is that you can run it in any data set. You don't need to have a model, and that would give you a lower bound. And you can just write like a statistical test for this, like a Monte Carlo approximation certificate. Like if you take your data, you take a subset, you formulate an hypothesis test, and then you want to prove with certain p-value that the expected value of the SDP is greater than some bound. You can just design this hypothesis test using, for example, Markov's inequality, and it tells you what is the p-value of your experiment. Like when you take this, yeah. So, any questions?
I think you can have bounds on how close is this lower bound to the optimum in terms of the size of the sample and the bound on the ball that contains the data.
That would be great, yeah. And I think that would improve this result, right?
I
The
think
value of the K-means value or the SDP?
No, the K-means value.
I see.
The K-means value of the optimal solution for the sample, how close it is to the optimal K-means in terms of two parameters, the size of the sample and the radius of the smallest ball that encloses the data.
So the game here is to get a lower bound on the true thing, and we don't know how to get honest lower bounds on K-means values other than by passing to a relaxation, like the SDP.
Right.
Like we don't know how to solve
So in your case, you're assuming that you can solve the thing in the sample.
I can solve
Yeah.
on the sample optimally.
Yeah. So here, if you cannot solve in the sample optimally, but you can run this relaxation, that would give you a lower bound. Yes, exactly. And you can see, for example, what is the bound that you obtain for a mixture of Gaussians model. So, so here the number of points that you need. So if your Gaussians are in RM, and this is a simple model where you have two Gaussians with identity covariance, then you say the number of points that you need scales like L log m, and the bound that you get is like 3 times optimal. So it's a 3 with 99% confidence. Okay. And that is just only running like 7 experiments. So if you put more experiments, and I mean, this result is definitely not optimal, just like something that you can get. You can get a 3 approximation. And you can extend this, so you don't use Markov's inequality. You can use something smarter, like some concentration. And then in that case, then you can consider, okay, so you can consider some, okay, so in order to use this concentration bound, you need to know a bound on the value of the SDP in the sample, and you can just make it in a smarter way. So you take the minimum of the value of the SDP and the value of the KMeans Plus for the analysis. So this number is smaller, and you can get a lower bound still. And given a computational time budget, you can optimize the number of experiments and the number of samples to certify the largest lower bound that you get for a possible p-value, or you can optimize the best p-value for a given bound in the same way, and that is something like that you can do on your data. Like, just I want to show that my data is like, I want to see how good this lower bound is for this specific data. And this concentration that we use here will actually give us an additive bound instead of a multiplicative bound. So we can know that the value of the k-means is going, in the case of the mixture of Gaussians of k Gaussians, you can say that the value of the k-means is within like 8k plus 5 of optimum. So this is additive with, this is good in the, when the regime, when the dimension is large. Yeah. Yes?
Sorry, it's additive, like when you scale the points by 2, what happens?
Yeah, I mean, you bound.
Yeah, this is assumes that the covariance is at identity, yeah.
Right. That everything is a unit ball or something.
Okay.
And then it scales with the ball that
Yeah.
captures the data.
Yeah.
Got it.
Yeah, of course. Yeah. So I want to show some plots. So this is the example with the mixture of 2 Gaussians. So here we have a histogram for the values of the SDP in the samples, with the number of samples is equal to 10. And here we have, okay, this is for like the frequency of 3 is like 5 times, and the frequency of 1 is like 20 times for the value of the SDP. And this is the value of the SDP in the whole set, and this is the value of the SDP, the expected value of the SDP among the samples, right? So when we increase the number of samples, we expect that the value of the SDP, the expected value of the SDP in the samples will get closer and closer to the expected of the value of the SDP in the whole set. So this concentrates like that. And we actually find that the expected value of the SDP is smaller than the value of the SDP in the whole set. So that's something that we don't know how to prove, but it's something that we observe. And
like from NIST over many data sets? From NIST specifically or on many data sets?
We've never seen it not satisfy the
Okay.
goal.
And then, for example, this. So here we have, for some data sets that are used in the KMeans Plus paper, we have the lower bound that for this number of clusters, we have the KMeans Plus minimum over several iterations. This is the lower bound that we obtain with this technique. And this is the lower bound that we that comes from the KMeans Plus with the expected value of the initialization. And this is the number of experiments that we perform. And we optimize for a specific time budget. So we say what is the number of experiments and the number of samples for this specific time budget. And So here what we observe is that the actual bound that we obtain is sometimes is very close to the value of the KMeans plus, and is much better than the other lower bound. But sometimes in this example, what happened was like the SDP solver that we were using did not output something that was feasible. So in many of these examples, the SDP solver didn't output something that was feasible. So we had to round it to a feasible point of the semi-definite program in order to produce a lower bound. And in this case, when you round it, the lower bound that you get is
so it's
not meaningful.
It's an issue of the solver.
So it's an issue of the solver, but it is an issue that happened with many solvers that we tried. So and these data sets are supposed to be not actually clusterable. So yes, yes. Mm-hmm. Well, supposedly, that's the yeah.
How many points in the integers in 50?
I don't know.
I'll look it up for you.
Mm-hmm. So this can tell you that your data is clusterable, but you cannot tell you that your data is not clusterable, right? That's what it does. And so I'm done. Okay, so some open problems that we're looking into. So the first thing that I mentioned was that the expected value of the SDP in the sample seems to be a lower bound for the value of the SDP, and we don't know how to prove that, and also we don't know if this is true for other SDPs. And in general, if we can do certifiers of these lower bounds for other SDPs, may be very useful. But here we are using the structure of the KMeans, the lower bound that you mentioned, and so we don't know if that would be true for other problems. And say if we can have an approximation of the number of mistakes instead of the value of the KMeans, and just do smarter sampling than what we are just doing now. And this is it. I have some references, but in fact, I should have only left this one. That is the one that we discussed just now.
So, thank you.
So I should suggest that you compare this algorithm that you have. This algorithm that we have it for clustering and hierarchical clustering called affinity clustering. That is the algorithm actually was in NIPS previous year. And there is a Google research blog on it that is done with Google essentially and Google data. It is currently in use maybe, 10-15 places at Google. That's the main clustering algorithm at Google. It works at scale, means 12 trillion edges. We are clustering less than a minute. And I think you should take a look at it essentially.
So what is the objective that is optimizing for?
Essentially the idea is that you want to cluster. So the way the one that we have done it in particular in practice, we have several theoretical results as well. But the one that we had label data. We just essentially stripped the labels, gave this algorithm, we compared it with K-means or other things, and even in smaller data actually outbeat those algorithms, like single linkage or average.
But that's not it's not a clustering problem. You have labels, you try to find sets which are homogeneous with respect to the labels, and you don't know how the labeling was generated, right? So yes. For any clustering algorithm, I can give you data for which this clustering algorithm will look optimal under this criteria.
What do you mean optimal? This algorithm that
you give me two algorithms, tell me which one do you want to be the other, I'll give you a data set in which this one is.
No, I didn't generate this. These are currently in use at Google. I didn't generate. Yeah, I'm doing enough theory and practice. When I claim something, I know what I'm talking about. So that works in practice. For lots of this objective, that actually outperforms lots of previous algorithms. And you may try yourself. If you don't believe it, just try it. But as I mentioned, there's a Google research blog on it, affinity clustering, and it is the main clustering algorithm at Google. So take a look at it if you want, essentially.
But it has label data?
But that?
Yeah,
But some of the data is labeled?
Yeah, I mean, so essentially that's the thing, I mean, that I talked with Yuri Laskovic, I mean, we got some of the data from his, so we want to see, I mean, practice which, so we have some theoretical things about the, essentially the algorithm, and the algorithm is very simple algorithm based on the Brufka algorithm, Brufka minimum spanning tree algorithm.
So it's like single linkage, basically.
No, it's not single linkage. That's
like Kruskal.
It's Kruskal is single linkage, Brufka is not single linkage. And we are comparing it with single linkage as well, and average linkage. And it outperforms like a lot essentially the things. I mean, take a look at it, I mean, you will, I was like quite surprised actually with the things that we have in there.
Yeah, there was a question here.
I'm sorry. Yeah. Yeah. What?
Yeah, I think I mean, it would be good actually. I will be very glad, I mean, because I didn't believe it actually that works, and this is like the current. The other people tried at Google KMeans or KMeans Plus,
it sounds
none of
pretty
them
cool.
actually
Yeah.
work, and also for the huge data. So I think that is. I mean, still we are thinking more about this to get more theoretical insight why it works so well. But it would be, I think, nice to, I mean, compare lots of this kind of SDP algorithm with those algorithms as well, essentially.
So are there some more constraints you can throw into the SDP to try and get it closer to the, because I guess that's a gap that you can't get around even if you make S large, right?
Yeah. So for example, if you, we are relaxing the projection into the indicators with this SCP, but a priori you can do like a higher level relaxation for that set.
There's also the identity constraint we never use.
What identity
Projections
constraint?
are always less than or equal to the identity, and that doesn't appear in our SDP relaxation. So you could throw that in and see.
No, but I think that the solution that you obtain has all the eigenvalues smaller than 1. So, yeah.
So this is somehow falling kind of between theory and practice. And if you only care about the theory, then instead of doing the SDP, solving completely the K-means over the sample is still sublinear, because the size of the sample is independent of the size of the data.
Yes.
So even if I solve brute force and find the optimal over the sample, I'm still constant time, because the size of the sample is independent of the size of the data. It only depends on how well I want to approximate.
But in practice, it may happen that if you do a larger sample and you run the SCP, you get a better thing than the smaller sample and you just run the K-means at the same time. But yes.
It's an interesting trade-off, right? Like
I'm
approximating the approximation, but how are the approximations?
Right. But I'm just saying, if you look at it from theoretical point of view, it's constant time.
Yeah.
It's true.
Okay, let's thank Soledad again.
Rachel, the intrusion data set is 500,000 data points. Our sample is 300.